For the three-dimensional shapes, we're going to be looking at volume and surface area. One way to get to know them is simply to memorize them.
I'm going to give you a few tips on how to better memorize them. Hopefully it will make the process a lot easier for you. So first, let's look at the volume of cylinders and prisms. In case of a cylinder, my volume is going to be the area of my base circle, so that's just pi r squared, times the height. So it's almost like my circle being stacked on top of each other as it goes all the way up through the height. And that is the volume of my cylinder. Analogously, the volume of a rectangular prism, which is essentially a box or a cube to the layman, it's the area of my base again, which is a rectangle in this case, so that's length times width, times, once again, the height. So it's almost like that area stacked on top of each other, like newspapers piling up, that create my full volume of the rectangular prism. And analogously, same for the triangular prism, only in this case, my bottom shape is a triangle. 1/2, in this case, I'm calling it length times width rather than base times height, but that too, multiplied by the height, stacked on top of each other, generates my full volume for the triangular prism. So all these basic core shapes have the same approach. It's area of the base times the height. Now the surface area is a little more differentiated. For example, on a rectangular prism, it's going to be simply the two-dimensional area of all 6 sides. The 6 sides are broken out into 3 pairs of the same sides. One's length times height, one's length times width, and one is width times height. So it's the sum of 2 times each of those for the surface area of the rectangular prism, for example. Analogously, it would be same for the triangular prism. You just have to figure out what your hypotenuse there is in that case and take the same approach. The cylinder, the same idea. We want to calculate the two-dimensional areas around all the surfaces. So I have 2 circles, my base and my top. That's 2 times pi r squared, the area of a circle, plus if we unfolded the can of the cylinder, pretend it were like a Campbell soup's cover on it, and we peeled that off and we laid it down flat, I'd essentially have a rectangle. The height would be h, and the length would be the distance around my circumference, which we know is 2 pi r. So the area of that long rectangular label unfolded would just be 2 pi r times h, my length times my width. So that's the surface area. So great, we have the basic shapes. We understand how the volume's calculated and even the surface area, even though that's less consistent. What do we do when we get the following shapes? A cone that fits perfectly within my cylinder, so it has the same height and the same base. Or perhaps a pyramid, which sits exactly within my rectangular prism. It's a 4-sided pyramid. What's the volume of that? And how about a triangular pyramid where I have, like my pyramid before, a pyramid fitting perfectly within my triangular prism. But in this case, the base is a triangle. And away from the base, it only has 3 sides. What is the volume of all of these? Well, it's quite easy, actually. They are all 1/3 the volume of the corresponding cylinder or prism. So if you remember that, you can quickly, knowing your cylinder and your rectangular prism volumes, you can quickly calculate your pyramid and your cone volumes. So the cone is going to be 1/3 pi r squared h, where r is the same base as the cylinder and h is the same height. The rectangular prism will be 1/3 length times width times height. The triangular prism will be 1/6 length times width times height, each of which is multiplied by 1/3. So that is our key for memorizing the relationship between cones and pyramids and their cylindrical and prism shapes. How about a sphere? If I put a sphere within my cylinder, just such that it perfectly touched the sides and perfectly touched the bottom and top of my can or my cylinder, what would the volume of that sphere be? Well, the number to remember in this case is 2/3. The volume of that cylinder is going to be pi r squared times the height, but my height, as I can see here, is 2 radii of the ball high, so it's 2r. So the volume of my cylinder is really 2 pi r cubed. And if my factor for the sphere is 2/3 in this case, that would mean my volume of the sphere will equal 2/3 times 2 pi r cubed. And that's actually the case. The volume of the sphere is 4/3 pi r cubed. And likewise, the surface area of my cylinder was 2 pi r squared plus 2 pi r h, where again h is twice the length of the radius. So for the cylinder, that's 2 pi r squared plus 2 pi r times the height, which we know is 2 times the radius in this case, because the ball's fitting perfectly in the height, and the ball is 2 radii or 1 diameter high. So that in turn is 2 pi r squared plus 4 pi r squared, which just equals 6 pi r squared. And if we multiply that by 2/3, our factor for a sphere, that becomes 4 pi r squared. And sure enough, that is the surface area of the sphere. The sphere volume is 2/3 the volume of the cylinder into which it fits perfectly. The surface area of the sphere is also 2/3 of the area of the cylinder into which it perfectly fits. So all you have to remember is the volume of any cone or pyramid is 1/3 the volume of its corresponding prism or cylinder. Likewise, the volume surface area of a sphere is 2/3 the corresponding cylinder volume and surface area. So hopefully that helps make it easier. And in either case, you could potentially memorize all the individual formulas themselves. We saw in the last lesson when we multiplied the length by a scale factor, and that could mean doubling it, tripling it, or even cutting it in a half or a quarter, multiplying by a quarter, for example. If we did that, we knew the new area of our two-dimensional shape, regardless of the shape, square, circle, triangle, or blob, as we looked at it, would increase. So my new area was that scale factor squared times the original area. If I doubled my lengths, for example, my area of the shape would increase to 2 squared times the original area, or 4 times my original area. So now we're looking at three-dimensional shapes. What do we think the relationship might be for three-dimensional? Not entirely surprising, since a volume multiplies 3 different lengths together, we need to cube the scale factor to get the new volume. So for example, the new volume will equal the scale factor cubed times the old volume. So if I doubled my side lengths on a cube, for example, the new volume of my cube would be 2 cubed, or 8 times my original volume. Let's take a look at that, say, for a rectangular prism and also a sphere, just to confirm that that's the case for different types of shapes. So my rectangular prism, I know my volume equals length times width times height, and my new volume, I'll call volume prime, equals, well, I've doubled my length, I doubled my width, and I doubled my height if I was scaling all the lengths. That in turn equals 2 cubed times length, width, height. And I know length, width, height is my original volume, so I can substitute that back in, and my new volume equals 2 cubed, 8 times my original volume V. How about for a sphere? Well, we just learned the volume of my sphere is 4/3 pi r cubed. So in this case, I will again double my length, unit of length, the radius in this case. So my new volume will be 4/3 pi times 2r is my new radius cubed. And that in turn equals 4/3 pi times 8r cubed. And I could rearrange that to say that's 8 times 4/3 pi r cubed. And I know that 4/3 pi r cubed is my original volume. So I can substitute back in my original volume. And I know my new volume, V prime, equals, again, 8 times my original volume. So even for a very different shape than a cube or a box, a sphere, and again, this will be true for any shape, as I increase or decrease my lengths by a constant scale factor, my new area of a two-dimensional shape becomes my scale factor squared, and the new volume of a three-dimensional shape becomes the scale factor cubed times my original volume. Again, a useful relationship to know for many types of problems that they'll give you on the exam.